All right, so regarding the question in the chat, you're supposed to set the power supply voltage to 1 volt, peak to peak. If you measure it with the multimeter, then you're going to be measuring the RMS voltage. That's all it is. And you should record that. Okay? I mean, on the scope, it's going to be 1 volt peak to peak, but on the multimeter, it's going to be about 0.35 volts, that ballpark. Okay? But you should record that. Okay? All right. So I'm based on that, I guess I'm assuming everybody can hear me. So today what I want to do is really, I want to finish up on AC circuits. So if I were to write my objectives for today's lecture, I'll finish up on AC. And then talk about transformers. One can spend a long time talking about transformers, but because this is an introductory course in physics, we're going to talk about it briefly. We're going to make several approximations. Okay, so you're not going to be looking at the real system, but something idealized. But before I go on, just 1 second. I just have too many windows open. But before I go on, the other day I promised you to show you how the units come out for X sub L and X sub C. Okay, so X sub L was, we define X sub L, the inductive reactance, as omega times L. Omega has units of 1/seconds. Radians is not a physical unit, okay? And then L has units of ohm seconds. We established that in the previous chapter. So 1/second times ohm seconds gives you ohms. And then for capacitive reactance, X sub C was 1/omega C. Again, omega is units 1/second, but C is a coulomb per volt. And if you multiply these together, you get 1/an amp per volt, which is a volt per amp. That gives you ohms. So these you get to see where the units come from. Questions on that?
I have a question.
Sure.
It is not on the units. For the Rlc circuit, when the X sub L is equal to X sub C, does that mean that the circuit behaves in a way as if the inductor and capacitor was not present?
Correct.
Okay.
I mean, from a standpoint of voltage, right? I mean, there's still a voltage drop across the inductor, and there's still a voltage drop across the capacitor, but they're equal to each other.
Mm-hmm.
But they cancel out, right?
Mm-hmm. Yeah.
And so basically, the voltage drop across the resistor is the power supply voltage.
So is it like a circuit, like a multi-purpose circuit, therefore they use it?
Oh, you mean the applications of it?
Yeah, like you can change things as if only a resistor was present, and you can change things as if all the three were present, or if one was dominating over the other.
Yeah, so they're used for filtering out frequencies.
Mm-hmm.
So if you're using it to tune to a particular frequency, you want like we said in lab, a high Q circuit, so that when you plot either current or charge as a function of omega or F, you want this to be very narrow. That's not a good graph. But you want this to be very narrow so you'll pick out that frequency. I mean, you can't get it, you can't make it the width 0, but you can make it very narrow. Okay. You can use voltages across different combinations to filter out certain frequencies. There are things called notch filters that use an RLC type circuit. Okay. And so there are a lot of different applications for this circuit. That's why we spend a lot of time just on this particular circuit.
And for like when they say that X sub L is greater than X sub C, or the other way around, and they say like it is more inductive or it is more capacitive, I'm kind of confused as to what the circuit is behaving like at that point when they say it is more inductive than capacitive.
So my next slide will answer that.
Okay. All right.
So I just wanted to show you this impedance triangle, because this triangle that you see in that slide in the corner, that kind of summarizes really everything about the RLC circuit. If you multiply the length of each side by I, that gives you the voltage drop. Okay, so if you take I times Z, that's the power supply voltage. You take I times R, that gives you the voltage across the resistor. You take I times X sub L minus X sub C, that gives you the voltage across the combination of the inductor and the capacitor in series. And we got to be careful in terms of what you're measuring. You know, I've always been drawing my circuit like this. Okay. But if I switch these two around, oops. Now you have no way of directly measuring, sorry, I'll label these because this is a bad picture. There's no way of measuring directly the voltage between, oops. Let me redo that. There's no way to measure the voltage between the inductor and the capacitor now, right? Because if I measure the voltage between these two, these are 90 degrees out of phase. Okay. The only way to get to really see the X sub L, X sub C, actually to physically measure it, okay, because what we wrote in that triangle is different from what we can measure. If I want to physically measure the voltage drop between X sub L and X sub C, I actually have to have them in order. Now this is V sub L minus V sub C. Okay? All right, so let's write a couple things on our tangent of phi was equal to X sub L minus X sub C over R. And the voltage across the resistor was the current times R, which is equal to and let's say V sub L.
Should there be an additional R?
Yes,
okay.
Thank you. And for a V sub C, I put a V sub C there, I mean X sub C there. Okay, so the question is, you know, what does phi do? What are the different possibilities for phi? Okay, if this is bigger than this, then the phase angle is positive. Isn't that true?
Mhm.
In other words, I mean, and then you can vary that based on the frequencies. So at frequencies at which this is bigger than this is positive, that means that the voltage across the inductor is greater than the voltage across the capacitor. So the inductor dominates. And the current will lag the voltage. And so the phase or the phasor diagrams I have been drawing represent the case where X sub L is greater than X sub C. The inductor is dominating over the capacitor, so it's inductive. So that kind of answered your question, Ratesh?
Yeah, it is just that I cannot like physically see what that means in the circuit, how the circuit behaves, like as if the capacitor was not present, or
No,
like.
it just means that the voltage across the inductor is bigger than the voltage across the capacitor. That's all.
Okay.
That's all it means, right? Because it plays a more dominant role in the circuit. This will be bigger, and at lower frequencies, that's going to be the case.
Mhm.
I'm sorry, at higher frequencies, that's going to be the case. My bad.
Yeah.
Sorry. If this is 0, X sub L equals X sub C, that means the voltage across the inductor is equal to the voltage across the capacitor. And the voltage across the resistor is equal to the power supply voltage. That's resonance. That's the resonance we've been talking about. Okay? Now, if X sub C is bigger than X sub L, this angle is negative, the capacitor is dominating. The current will lead the voltage. And so the phasor diagram, then, when I draw the phasor diagram, when X sub C is bigger than X sub L, then my drawing will look like this. I think you know what I'm going to do next. So this is V sub R. I'm just going to make X sub C longer, or V sub C longer, than V sub L. And then I'm going to use my terrible color. I'll make it really thick so you can kind of see it. Well, actually, this is V sub C minus V sub L, but whatever. And then this is phi, and then this is V sub M, or the supply voltage. And so now the current, which is this green one, is leading the voltage. So the capacitor is dominating. It just means that this V is bigger than the V across the capacitor is bigger than the V across the inductor. That's all it really means. Okay, so those are the three conditions on the phase angle. Chase, we will. I'm going to do some fun ones. I'm going to try to do some fun ones today, okay? I'm glad you asked that. So Chase, the only thing is that when I start making the circuit more complicated, you will see that the phasor diagram is useless. I mean, it's too cumbersome. I shouldn't say useless, but it becomes too cumbersome. And then writing everything in terms of not pictures. Instead of drawing pictures, we use phasors, but they're written. Everything's written in terms of complex exponentials. It makes life a lot easier. Physicists will write it in terms of complex exponentials. Engineers will write a little bit differently. Okay. And you probably learned that when you take Engineering 17. Okay. So before I go in and talk about the different kind of circuits, I want to talk about power in an AC circuit. There's no power losses in pure capacitors, and there's no power losses in pure inductors. Pure means ideal. Obviously, that's not the case. So really, any power loss in these circuits is due to the resistor. So I'm going to show that. Let's write the expression for the power in the LRC circuit. Let's start with P is I times V. And so we're going to work now in the time dependent. We're going to look at a time dependent formula. We're going to be in the time domain now. Okay. These expressions are all in the frequency domain because I can write everything in terms of frequencies. But now I'm going to go into time domain. And let's write the expression for power. I'm going to be very general. I want the total power dissipated in my circuit. So I is the total current, which is phase shifted, times the power supply voltage. Okay? We'll start with that. So let me pull out the I and the V. And of course, I could write this as I times R too, right? I mean, okay, so cosine omega t minus phi. All right, so that's power as a function of time in my circuit. I want the average value of this thing. Now, in order for me to calculate the average value and to make the math a little bit easier, I'm going to expand this out. Cosine, cosine, sine, sine, right? And I want P average. So I got to integrate this from 0 to whatever my period is. And then I got to divide by the period. Now, cosine times sine is an odd function. If I integrate an odd function over a symmetric interval, the integral is 0. Okay? This integral will be 0. Oops, I forgot a dt. And then cosine times cosine integrated. What's the integral of cosine squared? Well, what's the average of cosine squared? Well, it's a half. And so P average then, when you perform the integral and divide by the period, will give you that. Okay, so that's the average power. But this can just be written as I max over the square root of 2 times V max over the square root of 2 cosine of phi, which is I RMS times V RMS cosine of phi. That's the average power dissipated in my circuit. Cosine of phi is called a power factor. Okay, cosine of phi is called a power factor. What is cosine of phi? Well, let's look at our impedance triangle. This is V sub m. This is V sub L minus V sub C. And then this is V sub R. Isn't cosine of phi, and I'll get out of the way, V sub R over V sub n? In fact, I can make these RMS values if I wanted to. Okay, so what are we going to do with that? This is I, R, RMS, times R. Let me take this and put it in here. What do you think I'm going to get? If I substitute this thing into here,
you'll end up getting I RMS squared times R.
Yeah, that's what we'll get. And this shows you that the average power loss is all due to the resistor. Okay? It's all due to the resistor, and it's dissipated as heat. It's kind of a neat way of showing that. Your book discusses it. Just 1 second, I misplaced something. Okay. Are we okay with that?
And we could do that because they were in series.
Yeah, we are analyzing the series version of the circuit. Mm-hmm. But in reality, if they're in parallel, you're going to see that the power loss is just due to the resistor. You're not going to get any power loss due to the capacitor and inductor, even if you got a parallel circuit. Because the equation probably look a little different. This expression would look different for a different circuit. But in the end, you'll see that the average power loss in the cycle is all due to the resistance. Okay. So we see that I is frequency dependent, which we've said before. And again, we're looking at the current in the frequency domain. Hold on a second. So I can just make the screen like so. And the current is maximized when X sub L equals X sub C, and then we call that the resonance frequency. Okay, and that we've discussed. And again, this is reviewing what we've talked about before, that the resonance frequency, we talked about this in lab, is basically, or the angular frequency. I got to be careful. A lot of times in physics, we're not careful discerning the angular frequency with the frequency itself. But omega naught is 1 over the root LC, and F is 1 over 2 pi root LC. And this is the natural frequency of oscillation of the circuit. And so, like we said this morning, the current maximized when omega equals omega naught.
Is it the frequency of an LC and not an RLC?
I'm sure. I'm sorry, but why was that?
Oh, you want me to repeat the question?
Well, it's the same, right? I mean, for either circuit, it's the natural frequency of oscillation, though, right?
Yeah, I mean, I was just asking if like it is same for the RLC, right?
Yeah, it is, right? I mean,
Okay,
it's exactly the same.
Mm-hmm.
Yeah, because the R is not going to the R is not going to affect it. And in fact, I'm going to do a parallel one, and the natural frequency of oscillation will have the same expression. Not all three in combo in parallel, but there's one related to the homework I want to show you. This is the expression for the current. This is the plot of the current as a function of omega. And I'm plotting it as a function of omega instead of F, because if you write everything in terms of F, you have to write 2 pi's everywhere in the equation, which is kind of cumbersome. Okay? And I've done it for 3 different values of R. One is 10 ohms, one is 5 ohms, one is 3.5 ohms. And what you see in the graph, as the resistance gets bigger, the graph gets wider. And actually gets more asymmetric. It gets more symmetric as R gets smaller. And it's hard to tell that, but when you do your data, when you do your graph, your R is going to be around 50. And so you're going to see the asymmetry in it. And you'll see the current rise up fairly quickly, but then it drops off very slowly. And I chose a weird value for omega naught. Okay, it's 10 million. Okay, that's a kind of a high frequency circuit. Let's take a look at the expression for power. Now, I should go over and write the expression for current that I wrote this morning. This morning I wrote the expression for current and it looked like this. By the way, Ravtesh, regarding your question with the natural frequency of oscillation, I'm going to do a parallel circuit, but only the resistor, only the capacitor and inductor will be in series. And you'll get the same natural frequency of oscillation, but then if you start getting more complicated, things will be different.
Okay.
Okay. But yeah, adding the R is not going to make a difference in the Lrc circuit as opposed to the Lc circuit.
Is the reason because the resistor is always in phase with the power supply?
Yeah, you can say it that way. I mean, you can couch it that way. You can say it a different way when when you analyze it in terms of complex exponential, because the resistance is always treated as something real when you actually do the analysis in complex exponentials. And I think what you said is perfect, is actually might be better. But when you talk about how the capacitor and the inductor behaves, it's always treated like an imaginary number. And so they're actually completely separate. And it really is because of the fact that the current through the resistor is in phase with the voltage across the resistor. Yes. Mm-hmm. Okay. All right. So let me write down the expression for I. We wrote this morning.
Can I ask one more question?
Sure.
I read it somewhere. They said that for high enough frequencies, the resistor actually goes out of phase from the power supply.
Yeah, so when you start getting to extremes, the resistor will start exhibiting either capacitive effects or inductive effects. Mm-hmm. Okay, No components are ideal. So when you start going at extreme frequencies, you have to worry about what are called, parasitic capacitance or parasitic inductance in any component.
Mm-hmm.
We're not going to look at those here, but if you're, electrical engineer, you do have to worry about that kind of thing when you're at very high frequencies. And we're not going to worry about that here, though.
Mm-hmm.
Okay. So I wrote this morning in lab. So I want to look at the equation for power now. Okay. Yeah, in the real world, things aren't ideal, but when you push things to extreme, you will see the non-ideal situations. Even with mechanics, right? With mechanics, you're not going to. The laws of mechanics are not ideal. When you start going to close to the speed of light, you have to change things, right? And the same thing.
Yeah. They're also talking about something called the skin effect of resistor. Like the current tries to run on the surface. And
Yeah.
Yeah.
So same thing with, and you'll see people do these demos. At very high frequencies, the electromagnetic signal will not penetrate your skin. Or I shouldn't say will not penetrate. It won't penetrate your skin very deeply. So you'll see somebody, you need a special power supply for this, run the signal generator at 120 volts, hold the light bulb in their hand, light bulb goes on. They don't feel anything. They run at 100,000 hertz. This is the skin effect. High frequency signals will not penetrate, or won't go very far into your skin. And you can actually, as a junior level person, you can in physics, you can solve that problem and derive the expression for the what's called the skin depth.
Mm.
But we won't deal with that here. Okay, let's look at the equation for P average. Okay. And if I want to make this an RMS value, I just got to divide this by the square root of 2, or I can make this VRMS. Okay. So this expression, because I'm going to save time in algebra, I'm just going to take this and write it and square it. I got to square the denominator. So this is the expression for power. I can also factor out the L if I wanted to. And sometimes you'll see the expression with the L factored out. Okay. And your power is maximized again when omega naught equals, or omega equals omega naught. In other words, what this means is, and I said that this morning, the energy delivered to the load is maximized at omega equals omega naught. That's the frequency the system wants to oscillate at. So you get actually, even though you get maximum energy delivered to your load, you also get maximum energy lost because the current through the resistor is maximized. Does that make sense? So here's a graph of power. What the power looks like. It's really a graph of that function for some chosen value. Again, when you see R gets bigger, the graph gets wider. Okay. And again, I chose a weird value for omega naught. Now, we can define Q as the quality factor. The quality factor is defined as the maximum energy per cycle divided by the energy loss per cycle. And so what I'm going to do is I'm going to show you, I'm going to derive the expression for the quality factor. So Q is 2, actually I forgot the 2 pi. Is 2 pi times the energy, the maximum energy in a cycle, over and it's evaluated at omega naught. Well, the maximum energy in a cycle is what? It's 1/2 L I max squared. The energy loss per cycle is, how am I going to get the energy loss per cycle? Well, it's going to be the integral of the power loss hold on a second. Per cycle. But we know that the average that's lost per cycle is 1/2 I squared R. And the average is 1 over the period times the integral from 0 to t of I squared R dt. That is the maximum value. So this is just this guy times the period. The 1/2s cancel, the i's cancel. And what am I left with here? I got Q equals 2 pi over T times L over R. And this is evaluated at the resonance frequency, so 2 pi over T is what? Omega naught L over R. That's the quality factor. Now, if you plot P versus omega, you can show that Q is also omega naught over delta omega. If you plot this, you can show that Q is the square root of 3 omega naught over delta omega. Okay, the width of this graph is different than the width of this graph. In fact, that one's wider. Okay, so I have a video in the modules where I show you where this comes from. Okay? And you can do the same derivation for that as you do for this. So if you watch the video, I expect you to watch the video that I put in the modules. For the lab, though, I put them in the lab module. I derived this expression, and I show that it's equal to this. Okay? This is a defined quantity, and from that definition, we get this. And again, this delta omega is the full width at half maximum. So basically, it's the two frequencies, the difference in the two frequencies in which the current or the power is half its peak value. Okay?
Professor?
Yeah.
Can you go over how did we know that the maximum energy in a cycle is that of the inductor?
Well, it's either the inductor or the capacitor. We can do it for the inductor or the capacitor, right?
So this is like the extreme case when it is in one of the two and it is not distributed in both.
Right.
Okay.
Right.
Mm-hmm.
So you have no charge in the capacitor.
Mm-hmm.
And the inductor has the maximum, the field is maximized in the inductor. And generally we write it this way in terms of the capacitance. I mean, you can write it in terms of capacitance too, but it's not done that often.
And does this energy include the energy that was lost in the resistor?
Only down here.
Okay.
Okay, it's only down here. But this does, I mean, the I sub n does include the energy that's lost by the resistor, right?
Yes. Mm-hmm.
Okay, so that accounts for it.
All right.
Okay, so let me do an example for the RLC circuit. We'll do some fun examples here. Okay, so notice how much stuff I can calculate for the RLC circuit. Obviously, I probably can't ask all this stuff for the exam. I can probably ask combinations of these. So you know, I expect you to know the RLC circuit inside out. Okay. And a lot of these calculations on this example are actually really easy. They are tedious though. Okay, so let's say I have an RLC circuit. And the resistor is 250 ohms. The inductance is 0.6 henries. And the capacitance is 3.5 microfarads. This is 150 volts. Okay, and let's let omega 377. Why did I choose 377? That's 60 hertz. What are the things we can figure out? I can figure out omega sub L, omega sub C. I can figure a lot of stuff right away. So notice the first few things I'm going to calculate are just maximum values. Okay, so we're looking at a fixed frequency. I'm not saying anything about the time dependence yet. And really looking at the circuit, looking at the time dependence of the circuit doesn't really add a lot, except that maybe you want to look at, on the scope. On the scope, you look at the time dependence of the circuit, you can see the phase shift clearly. And I showed you that in lab this morning. Okay, so what's X sub L? Well, X sub L is omega times L. And I have the number written down somewhere. $226. X sub C is 1 over omega C. I should have written it down, sorry. This comes out to be 758 ohms. So right away, which is going to be dominating in the circuit, the capacitor or the inductor?
Capacitor.
The capacitor is. And so the phase shift is going to be negative.
Mm-hmm.
So Z is going to be square root of 250 ohms squared plus this difference This comes out to be 588 ohms. By the way, X sub L minus X sub C, this minus this comes out to 588. I'm sorry, 532. Yeah.
Is that X sub L minus X sub C?
Yeah.
Okay.
Yeah, it is negative, right? So let me write it like that. But yeah, you're right, it's negative. What else can I figure out? The current. The maximum current is going to be our power supply voltage over our impedance. And this comes out to be 255 milliamps. What else can we figure out? Well, let's figure out V sub R. Let's figure out V sub L and V sub C. V sub R is going to be what? 0.255 amps times 226 ohms. And that comes out to be 64 volts.
I think you mean 250.
Oh, 250. I copied the wrong one, didn't I? See, there's too many numbers on the board. I actually don't like problems with that many numbers. Okay. V sub L is, now I'm gonna copy the right number down because I just wrote it down. And this comes out to be 57.6 volts. Now here's the interesting one.
Is that 0.255 amps?
Yes.
Oh, okay.
Right, because it's 255 milliamps.
Got it.
I know the dot's hard to see, sorry. And then V sub C, where's the value? Now check out this value. And that's possible. I'm still conserving energy. What else can I figure out? Well, I can figure out phi, right? I can figure out the phase angle. Okay, now I'm going to put the minus sign in there, okay? So phi ends up being I'm going to write it two different ways. You know why I'm writing it in radians? Because now I'm going to write the expression for the current. I'm going to in the circuit. I sub s, or I, is equal to V over Z cosine omega t minus phi. Oh, we already know what omega is, so I'm going to put in what omega is. Is that okay? V sub r V sub L. Remember, it depends on di dt. And then V sub C. Everything you needed to know about that circuit's there. Well, I didn't calculate power, but I think you can figure that one out. Are we okay with that? Actually, I've never done this problem in this kind of detail because I've never had time to do it. Okay. But everything you needed to know, and what you can do, pick a value for t and add these up. They should add up to 150.
Why is it a negative 57.6?
What's the, the current is this, right?
Yep.
And the voltage across the inductor is the derivative of this, right?
Yep.
And the derivative of the cosine gives you
Negative sign. Okay.
yeah, because remember the current lags the voltage.
So wouldn't V sub C be negative 2? Or am I just missing something?
You have to integrate this. The integral cosine the sine, right?
Yep.
Okay. And in fact, these two are 180 degrees out of phase, so it's got to reflect that fact.
Oh, okay, yep.
Okay. But you see, everything you need to know is there, right? But I don't, the time dependence doesn't really show me a lot. The Phasor diagram shows me more physics, but it's good to see both, both ways. Showing your V's this way is called the analysis in the time domain. And engineers don't really look at circuits in a time domain. They look at it in the frequency domain. All right, let's do a fun problem. Something that Chase alluded to. We have three components in parallel. This is actually a problem in your book. I mean, I didn't assign it for homework, but it's a problem in your book. I want to derive the phasor diagram for this circuit. So I'm going to erase this, if you guys don't mind. I'm going to draw the circuit here. And no, I'm not going to solve a second order differential equation to solve this one, because that would be tough for me. Okay, so resistor, capacitor, and in capacitor I wrote a L. All right, so what am I going to do with this? Drawing the phasor diagram will give you a lot of information about this circuit. And that's what I'm going to do. And this one's actually pretty straightforward to do. You just got to think about it. Like I said, if you have combos, series, and parallel, life gets a lot more complicated. By the way, I did screw up on your homework. I did have a more complicated circuit that I created, and I never put it in this homework assignment. I do want you to go through it. I'm gonna add it to the next homework assignment. However, I have a video that kind of discusses the problem. I'm gonna give you a link to the video. Okay, then you can go through it. All right, so I'm gonna draw a phasor diagram. So what do I know about this circuit? I know that the voltages are going to be the same, right? Sorry if I answered ahead of you.
You did.
Sorry. The total current is the sum of these, right? So, okay, I'll give you a chance to answer the question. Am I going to draw a phasor diagram for V or for I?
For I?
Yeah, I want to draw for I. They're different, right? Drawing a phasor diagram for V is boring. Because they're all the same. And I'm going to start with this one. Let's see. I want to start with this one just because I know that the current and the voltage are in phase. So and I'm going to draw that one in red. Actually, I'm not going to draw it in red. I'm going to pick a different color. No, I'll just stay with this because you'll associate it with the resistor. I've been doing that the whole time. And then the current is in phase with that, so I'm going to write above it. So now, if this is the voltage across the inductor, where's the current through the inductor going to be?
Is it below it?
It's going to be below, right?
Mm-hmm.
Because it lags. And what about the capacitor?
Above?
Above. I want to make everything in the first quadrant, so I'm going to make this one big. And so Maybe I didn't draw it tall enough. But this is I sub C minus I sub L. And this is the current, the total current. This is the phase angle. So tangent of phi is equal to I sub C minus I sub L over I sub R. Well, since all the voltages are the same, I can write it like this. Right? And the current, using the Pythagorean theorem, is that. And so I can write it in a different way. And I can factor out the V sub m. And so Z then so I have the expression for I. If I want RMS, what do I do here? I just divide by the square root of 2 here, right? I don't know why I wrote down RMS in the expression in the problem. So I created a slide with the phasor diagram at 2 different angles, at 2 different values of t's, and then a summary of everything that you need to know for the circuit. That wasn't that hard, right?
It seemed just like looking at the world upside down.
That's right. Let me, and I am running out of time, but I want to show you a couple of videos. Let's see. I want to do a similar circuit. Where is it at? It's not that one. It's this one. So let me set up this problem. And the phasor diagram for this one is very, very interesting. So I have a circuit. The video involves a circuit that looks like this. And this is actually a homework problem you have. And in the circuit, you were measuring the current through the resistor, the current through the capacitor, and the current through the inductor. Now, based on what I've done here, since these two are in parallel, what can you say about the current through the resistor? I'm sorry, the current through the capacitor and the current through the inductor? They're in opposite directions, right? Don't they tend to cancel out? What happens when the impedances of both these guys are the same? What should happen? If these two have the same voltage and they have the same impedance, guess what happens? They have equal but opposite currents. The current through here cancels. There's no current in here. And so that's what this video is going to show.
Of current and total current, and each leg shows 30.4 or 30.5 milliamps of current. You have to think about the phase relationship.
Sorry, let me start from the beginning.
The demo before you is meant to demonstrate phase relationship. In this circuit, if you follow this wire, we have the high side going into an ammeter, going to the top of an inductance substitution box, and into a capacitance substitution box. Each line here comes out into a ammeter for each, and then the bottom grounds are connected. So the ammeter on the left shows you the current through the capacitance leg. The one in the middle shows the current through the inductance leg, and the one on the right shows the total current. We have a AC source here set to approximately 1750 hertz, and this just shows you how can you have 4 milliamps of current in total current, and each leg shows 30.4 or 30.5 milliamps of current. You have to think about the phase relationship and think about how inductors have resistance themselves generating this small amount of current. As I adjust the frequency, and therefore the phase, you'll be able to know how the current changes for each leg. And if I adjust the frequency up, you can note the current change in each leg again.
So you folks have the actual, you can actually build these circuits. The only thing is you can't measure the currents. Okay. It would be nice if you had enough multimeters to measure all the currents at the same time. You'll get to see this effect. So, one thing I should leave up to you folks, you should draw the phasor diagram for this. This is an interesting one. It's actually, if you think about it, it's a very easy phasor diagram. You should try to draw that for practice. Okay? Draw the phasor diagram for that one. Let me give you another example. I am running out of time, but I love these examples.
Wait, the one you just drew isn't the phasor diagram?
No, this is the one for all three in parallel. That one's not. Look, I mean, this one has the resistor here. The one I drew originally had the resistor this way, right? I changed it.
Oh, yeah.
But still, I sub L and I sub C are going to be in the opposite direction. So let me give you one more circuit. And I have a demo for it. I mean, I don't have a live demo. Tyler made the videos for us. By the way, I don't know if you've checked out the Sierra College Physics and Engineering YouTube channel. He has all the videos there. So I have another demo I had to make with a light bulb here and an inductor. And another light bulb here and a capacitor. And so in the video, I had him adjust the frequency. If the frequency is low, right, remember X sub C and X sub L. If the frequency is low, this is small, but this is big. Very little current here, a larger current here. At low frequencies, then the bulb will go on. As I increase the frequency, this gets bigger, less current here, more current here, this goes on. So I have a video of that. By the way, you can actually set this up, I think, because you have the 2 light bulbs. You might be able to set this up with your lab kit.
So in this demo, we're talking about frequency dependence of circuits. On the left, we have an inductance substitution box set at 9 millihenries and a small light bulb. In parallel, on the right, is a capacitance substitution box and a small light bulb. We have a frequency generator generating a sine wave at approximately 70 Hertz right now. As you can see, all the voltage right here is on the light bulb, and as we go up through the frequencies, the voltage suddenly goes very dim on the light bulb for the inductance and very bright for the light bulb on the capacitance. We can go back down and we can see the transition between the two.
Okay, so another cool demo. All right, so I don't have a lot of time left, so let me this problem is completely solved in your notes, but I might talk about it later. I want to say something about the transformer. Whoops. The transformer, and granted, I'm going to go through this quickly. I apologize. The transformer is actually quite a complicated device. It is very important because it helps to deliver energy from the power stations to your home. It also has other applications. For example, if you want to connect, for example, an amplifier to a speaker, the transformer will help in terms of maximizing energy transfer between the amplifier and the speaker. Basically, it's a laminated iron core, and then some of them have an air core, but it's basically a laminated iron core with 2 separate circuits, a circuit on the left and a circuit on the right. The circuit on the left just has power delivered to the coil. The circuit on the right contains the load. So if we were to model this circuit, okay, if we were to model this circuit, by the way, do transformers work with DC power?
No.
No, because transformer work by Faraday's law, mutual inductance. DC power, current doesn't change, right? Or I should say battery power. Okay.
It only changes in the starting.
I'm sorry?
It only changes like in the starting.
Yeah, when you turn it on and that's it.
Mm.
Unless you use a square pulse, but you know, square pulse are a linear combination of sinusoidal functions. So if you were to model this, you basically would have your power supply on the left, and your power supply probably has some sort of impedance. Then the coil itself has an inductance. The coil also has a resistance. And then on the other side of the circuit, on the other side of the circuit, the secondary coil has a resistance and an inductance. And then you'll also have your load, whatever you're going to connect it to. Now, one can use methods, we're not going to do it, we can't do it here, but one can use methods to model your circuit as shown in the bottom diagram, where you have a source impedance, an impedance due to your coil, an impedance due to the secondary, and a mutual inductance, what connects the two coils together, and then your load impedance. And again, this is actually kind of complicated to analyze. We're not going to do it in this course. Okay, it would take me a whole class period at least to analyze this. So we're going to make some simplifying assumptions. Okay. In fact, if you put if with the iron core, it makes the analysis horrendous. Okay. So there's a lot of complications in the transformer that we're going to ignore. We're going to ignore eddy current losses. We're going to ignore issues with ferromagnetism. But here's the simplifying assumptions. We're going to assume that there's no heating or eddy current losses in the primary. We're going to assume that the flux through the primary equals the flux through the secondary. That's what the iron core does. We're going to have the iron core laminated so no energy is lost in the iron core. We're going to assume that the primary, the resistance in the source is negligible. That the left-hand side is just all inductance. Okay? And this is going to ensure that the average power loss is 0. The inductive reactance we're going to assume is way higher than any resistance that is on the primary side. So we're going to ignore any resistance of the power supply. We're going to ignore any resistance due to the coil on the primary side. It's all inductance. Whereas we're going to ignore any power losses. The power factor will be 0. And in the secondary side, the resistance of the load is going to be much, much less than the inductance of the secondary side. So everything is due to inductance. Okay? Now, on the primary side, the inductance is huge. There's a very small current going through the primary side. You can call it a magnetization current. Okay? So typically, because the inductance of the coil on the primary side is very large, there's a very small current. It's not 0, but it's very small current still. And that small current that's going through the circuit is changing, and then a small current is going to induce an EMF on the right-hand side circuit. It's going to induce a delta V2. Oops. Because the flux through each coil is the same, then the voltage across V2 is going to be related to the voltage across V1 by the number of turns both sides have. And so the ratio of delta V1 over delta V2 is basically the ratio of the turns. Because flux depends on, the total flux is n times the number of turns. I'm sorry, n times the flux through one coil. Sorry about that. And so for a transformer, ideal N1 over N2 is delta V1 over delta V2. But energy is conserved, okay, which means that I1 V1 has to be equal to I2 V2. The picture you see there, there's no load connected to V2. So there's very little current on the primary side. But guess what happens when I connect a load to V2? Guess what happens? If I connect a resistor across V2, what's going to happen? You're going to get a current, right? Go ahead, I'm sorry.
Is there more current?
You get more current in V1. Let me demonstrate that for you in a video. In this video, I have a transformer with a switch and a light bulb.
So in this demo, on the right, there is a variac attached to a 500 turn coil in series with a light bulb, a 100-watt light bulb. On the other side is a 23,000 turn coil attached to a rheostat and a single pole switch. You can see that the light is fairly dim, but once a load is applied to the other side of this coil with a switch, the light gets very bright. I can throw the switch again, and it goes dim again. Please see your instructor on how this works. Thank you.
Oops, sorry, I didn't maximize the window for you guys.
So in this demo, on the right, there is a variac attached to a 500 turn coil in series with a light bulb, a 100-watt light bulb. On the other side is a 23,000 turn coil attached to a rheostat and a single pole switch. You can see that the light is fairly dim, but once a load is applied to the other side of this coil with a switch, the light gets very bright. I can throw the switch again, and it goes dim again. Please see your instructor on how this works. Thank you.
So, hold on a second.
So in this demo,
So, I really didn't do this topic, or the topic of transformers, much justice because of time. So generally, and that usually happens in my class, I generally, one second. I ask a conceptual question on the exam regarding transformers. There's not a lot we can do with transformers. Because the equations that we have are pretty straightforward, are pretty simple. And so basically you have the equation for, one second. You have the equation governing the transformer, this one, and then the conservation of energy equation. We can also talk about maximizing energy transfer between the primary side and the secondary side. I haven't had time, I don't have time to go through it right now. I do have that in your notes though. Okay. So anyway, I just want to talk real briefly about the transformer. Really, I could probably spend a couple lectures on it if I wanted to. Okay, so I've covered everything I needed to cover for this chapter. I did skip out an example. Do you want me to do it? In other words, do you want me to do an example with a real inductor? In your notes. You want me to go over it? Okay. So you don't have to, those of you guys who don't want to stay, don't have to stay. This is actually one of the advantages of doing this online. I can actually go overtime. I can't do that when we're in person because there's usually another class coming in. Okay, I'm going to do an example with a real inductor. An inductor that has a resistance. Okay? So let's say we hook up this circuit. The power supply is 110 volts. You have an unknown inductance. And we don't know the resistance of the inductor. But we know the value of the resistor. And they're just in series. And we can analyze this with phasors. So basically my circuit is this. Okay, what we know is that the voltage across the real inductor is 90 volts, and the voltage across this thing is 50. What does that tell you immediately? What is the first thing that tells you? If you know you have 50 ohms, 50 volts. What can I figure out right away?
The current.
I can figure out the current. How much current do I have?
1 amp.
1 amp. I have 1 amp through here, I have 1 amp through here. So I want to draw my phasor diagram. So let's think about this. This is a real inductor, so in reality, there's some sort of resistance here. Like that. This voltage, well, let me draw my current. Let me draw my, my current for my circuit. And let me draw V. So this is, the green is I, it's 1 amp. And then the voltage across the resistor is this. What resistance is this?
50 plus that of the inductor.
Yeah. Now the resistance, the voltage across the pure inductor is this. That would be the voltage across the pure inductor. But the voltage, the voltage across the real one, is it this way? Or is it this way, or is it somewhere else? This 90 volts, how would I draw it on my phasor diagram? Would I draw it vertical? How would I draw it? This is just pure inductance. But it has some sort of resistance in it. And so the voltage, the 90 volts is this.
So even if we took into account the resistance in the voltage across the resistor, that vector, we still have to consider it to get the correct angle for L?
Yeah, I mean, because this is this is what we're measuring, right?
Mm-hmm.
This is the voltage across that's the voltage across this thing, which we don't know.
Yeah.
And I didn't draw this very well. And then this is the other 50 volts, right? And so that's that. And so that's phi. Right?
Mm-hmm.
Now, what is, I gotta be careful, too many purple things. Hold on a second. Let me draw this in blue. What is this distance?
Professor?
Yeah.
Is that dotted line, is that parallel to the 90 volt line?
No,
Oh, okay.
it's parallel to this one.
I thought that was like the real vector for the inductance voltage.
This one?
The 90 volt, where you have 90
Yeah,
volt.
yeah. This is the one, right? This is the total voltage across the inductor. Whereas you're asking about this one, right?
Like, shouldn't the V sub m vector be evaluated such that it goes to the point which joins to the bottom in the same fashion as the 90 volt one? Like, shouldn't it be like a parallelogram instead of connecting where it is connected right now?
Oh, you want to draw it like this?
Like, if you connect a line to the V50 plus R tip,
You want me to draw this line?
this line, but slightly to the right, like where it would touch the tip of the V50 plus R vector. On the bottom, like you have.
But isn't it
V50.
true that this plus this has to be equal to that?
Yes.
Okay, these are horizontal, right?
Mm-hmm.
And then, I guess my question is, why can't I draw this straight down? Why can't I do that?
The V sub m is a vector which is the resultant of V sub L and V sub 50 plus R, right? Or not?
Oh, you mean this one?
Yes.
Yeah, it's the resultant of these two. Oh, you're saying I gotta draw. Well, isn't it this vector plus this vector? This is the voltage across the real inductor, that's the voltage across the resistor.
So what is that vector then, which is which is at the origin? The bottom one, the bottom horizontal one.
This one?
Yes.
This is 50 plus R.
And that is the voltage across the resistor, the entire resistance of the circuit.
Correct.
But for V sub m, we take the vector for the inductor and the vector for only the actual resistor.
Yeah, because this is both, right?
Okay. Mm-hmm.
Right. So this is the voltage across the inductor and this guy. And then you just got to add it to the 50 volts.
Okay, that clears it.
Okay.
Yeah.
I didn't draw very straight, but that's supposed to be straight. But isn't this V sub L? And is that true? And isn't this phi? Well, if I know this is phi, I know this, and I know that. I can figure out phi using what?
Law of cosines.
Yeah, law of cosines. So this. Okay, I'm not going to write the units. I'm sorry. Hold on a second. Phi ends up being 53.8 degrees. So then, I get that. Well, if this is 88, oh, can I figure out V sub R now? V sub little r? V sub r is what? 65 minus 50, what is that? And if I have 1 amp going through it, what's the resistance of that this little guy? Why can't I think? Okay, here we go. I think it's getting towards the end of the day. I can't write things down anymore. So are we okay with that?
I have one question.
Sure.
So for the V sub L expression that you have on the board, is that the vector which does not take into account the V sub small r?
Yeah, this is pure. In the notes, I call this V sub Z. Okay. So maybe I should have labeled that V sub Z, and this is V sub L. So that's my bad. Sorry about that. So can I figure out L? Well, I have 1 amp here, right? Then isn't X sub L 88.8 ohms? And if 88.8 ohms is omega times L, then L is 88.8 ohms over 2 pi times 60. This comes out to be 0.235 henries. So I know the inductance. I actually know the voltage across the pure inductance. The other question is, what is the power loss? The power loss is going to be it's going to be 1 volt times 110 volts times a cosine of 53.8 degrees, and that ends up to be 65 watts. And this ends up being okay? Let's just show you the power of the phasor diagram.
That is 1 amp, right? On the top.
1 amp, geez. I think it's too late in the afternoon for me. Maybe I should not write that. I should stop dropping. I should drop the units so I don't make those silly errors. Okay. Maybe I'll ask you one more question. If you have time. If you want to stick around, I'll ask you one more, because this is related to the problem that I didn't include on this homework assignment. Suppose I have a circuit like this. This is ideal. What does the phasor diagram for that look like?
Professor?
Yeah.
If we just had to look at like the functioning of that circuit, would initially all the current pass through the capacitor and the resistor only?
You're talking about the transient response though, right?
Okay.
Right. But you're right though. Right, you're right. You're asking about the transient response, and that's true what you're saying.
Your camera just froze.
I froze. Okay, hold on a second. I have to turn it off and turn it on, then it'll work. Okay. So this will be the last one I'll do. And I'm hoping this will help you with some of the homework problems. So I want to draw the phasor diagram for this. What do I know? I know that the voltage across these two are the same. That the voltage across this and this has to be equal to the voltage across, I'm sorry, let me rephrase that. The current across the inductor and the current across the resistor has to be equal to the current through the capacitor. Right? The current through L and the current through R have to be equal to the current through C. Right?
Their sum has to be equal, right?
Yes.
Okay.
They're vector sum.
Yeah.
And this one's the total current. Right? This is the total current from the power supply. So I'm going to draw I sub C along the x-axis. That color you can see, right? Okay. Now, these two have to add up to this, but these two currents, how are they related to each other? They have the same voltage. Right? These two currents, these two devices have the same voltage. The current through the resistor is in phase with its voltage. But the current through the inductor lags the voltage across the inductor. And the sum of these two currents have to be equal to each other. So these two are 90 degrees apart. These two currents are 90 degrees apart. And so I sub R looks like this. I sub L looks like this. This is 90 degrees. The voltage through the resistor, the voltage across the resistor continues on. Let me make it longer. Is that. What about the capacitor? What about the voltage? What about the voltage across the capacitor? It lags this by 90 degrees. So the voltage across the capacitor should be like this, right? But I'm not going to draw it here because that's not going to help me. I'm going to draw it here so I can do vector addition. That's supposed to be a straight line. That's a C. And then the sum so I can call this angle beta, and I'll call this phi, because this is the angle between the total current and the power supply voltage. That's my phasor diagram.
I'm feeling like I'm in an arts class right now.
So now you have to do a lot of geometry to figure out things. I mean, you would be given some quantities, and then figure things out. For example, this V sub m sine of phi I think you can write as V sub C minus and V sub M cosine of phi. This is R or L. I'll put an R here. They're the same. You can start building relationships from using some geometry. Okay, and then you can move on from there. Again, it's just more practice, and then you can go on from there and do a lot of algebra and solve the problem. Well, of course, you got to be given a few things. Okay. Any questions in general? I know I've gone way over, but I just thought I'd add these examples. No questions? So on Tuesday, I'm going to lecture on chapter 34. It's basically throwing a bunch of equations at you. A lot of the stuff is plug and chug. Okay? Even the exam problem will be mostly plug and chug. You have to know some basic things, and that's it. Okay, because to go through the last chapter in detail, would this be a test level question? Probably only the phasor diagram, not solving it would take forever, Kathleen. I mean, this would be homework. This is the homework question I forgot to put on this assignment. I'll put on the next one, so I set it up for you. That's why I wanted to go through it. Okay, but the test level question for our purposes, no. That would take too long. But to draw the phasor diagram, you can do it. Maybe something a little simpler than that. Okay, but I would not ask you a question that complicated. It would take forever for you to solve it. Yeah, that was the one where I did the example, Chase. That was this problem where we talked about a little earlier. And I said, draw the phasor diagram. That one's actually very easy. That was way easier than this one. Okay.
Professor?
Yes.
How did we decide the length of V sub C going in the negative, like passing through that horizontal axis instead of staying on top?
I could have made it shorter, but then my picture would be cluttered.
Oh, okay. Mm-hmm.
That's all. I mean, you're right. I mean, I could have put it down to here, but then this blue vector, it would just be a mess.
Oh, okay.
Yeah.
Yeah. So we can do this as per convenience.
Oh, absolutely. As long
Okay.
as it's correct, right? I mean,
Mm-hmm.
yeah, and I think that's some of the issues students, because if you look at my fall 2020 lecture on this, a student asked a lot of questions about, why did I choose that orientation? Just for convenience, right? Because I think somebody asked me about choosing this, and that was just for convenience, right? Choosing it so it's this way, because I know that's the total current. I'll build everything from that.
Mm-hmm.
All right, so when you draw these, you want to find where you want to build from.
Mm-hmm.
Okay, and so since this involves the total current, I want to build from that.
And for the angles, we can just like take them any variables.
Yes, because they're going to be determined by omega, L, R, and C in general. And this is what I drew here is a very difficult question. In fact, when you take engineering class, you're not going to draw these pictures. You're going to do it in a much more powerful way. Mm-hmm. Okay. And I just go through this so you understand what this LRC means. I mean, not the LRC, but the phasor diagram gets you. Because otherwise, if you just do the LRC series one, you really don't learn much.
Yeah.
Okay, so I don't have anything else. You folks have a good weekend.
Thank you.
All right.